All right, in this video, we continue our work on truth tables using the conditional statement. So first, let's review what the conditional says and then develop our notation for it. So the conditional says, if one thing happens, if P happens, then Q has to happen. So if it rains, then there must be clouds in the sky. So raining implies clouds in the sky. Rain can't be falling from something that's not a cloud. So the notation for a statement like this is P arrow Q. The arrow is a pretty intuitive symbol, actually, in this case. If you see P happening, you follow the arrow, then Q will happen. Another way to think about this is for all situations times P is true, Q is also true. Q has to be true. So this is a way to write the universal, if you remember from 2 videos ago, universal quantifier. So conditional logic can be rephrased using universal logic, universal quantifiers. So let's look at an example. This is just kind of a way to get your feet wet and thinking about negating a conditional, which we'll get to more later. Suppose you order a jersey on Tuesday and you need it by Friday for Saturday's game. So the website says, hey, today, if I order the shirts with expedited shipping, I will receive it by Friday. Okay. In what case would this website be lying to us? We say if this is P, if P, then Q. Just think about this intuitively. When do you disprove the website and when do they show them wrong? So in this case, you have to pay for shipping. And if you paid shipping and received the jersey, you didn't disprove it. But if you paid for shipping and didn't receive the jersey, that's when you disprove this case. Now, if you didn't pay for expedited shipping, all bets are off. There's no guarantee, right? So this kind of intuitively makes sense. But if we start combining statements, we'll need some more formal rules for how to handle this. So here's the truth table for conditional. And I will again talk through it. I think when I first saw this truth statement, this truth table, I was a little bit annoyed or bothered by 2 cases. I'll show you this. P implies Q. If P then Q is a statement we want to understand. So again, let's look at all of our options. True, true, false, false, true, false, true, false. So if P is true and then Q is true, that was a condition we saw up here that's valid. If I bought the jerseys with expedited shipping and they came by Friday, that is demonstrated to be true. But if I bought the jerseys on expedited shipping and didn't receive it by Friday, if it's false here, the way to disprove that, this thing would no longer be true. It would be false. P does no longer imply Q, so that's false there. And these 2, I think you might be able to, this is what I experienced. These I understood pretty well. So take a second to make sure you understand why these values are such. The next 2 kind of bothered me. So if P is false, then there's no condition. Like if P is false, again, all bets are off. P implies Q is not disproven, so we say it's true. And if P is false and Q is false, we still say, hey, because P is false, there's no implication here. P implies Q is not disproven. So here is our truth table for P implies Q. And I struggled this with the first time I learned it. I just had to kind of take it at face value, like, oh, this is what it is. But I hope I've explained it in a way that you can buy on a little bit too. And so let's practice. What if we say something like, not P implies Q. Maybe I didn't pay for the jerseys and they did arrive. I don't know. Okay, so this could be some kind of statement that we want to analyze. So the way to construct it, PQ, we want P and Q. Oh, I should use R. Excuse me here. P and R. And then not P will be one of the little pieces that we have to analyze. And then that'll get us to not P implies R. Okay. And you can write it however you want, but I'm going to do it like this, just to make the logic a little bit more clear. This is an R here. So I'm writing this on the left and this on the right because it matches here. So, but I want to make sure I write P and R covering all options systematically: true, true, false, false, true, false, true, false. And then I can proceed to make not P the negation of these two. And now I want to look at when not P implies R. This is maybe the trickiest bit of this section. I have to now apply these two columns to what these two columns are. So if not P is false and R is true, that's like saying P is false and Q is true. This column this row corresponds to this row. So I need to put true in the corresponding not P implies R column. So I'll do another one. If not P is false and R is false, that corresponds to false, false here. And so the implication says, hey, it's true in that case. And if I go down to true, true, if not P is true and R is true, that corresponds to true, true. So the implication says P implies Q is true. So not P implies R is false, is true. Then the last case, here we go. Not P is true, R is false. That corresponds to here. P is true, Q is false. I have to say, in that case, the implication is false. So I hope I've explained this in a way that makes sense. If not, rewind and watch some of it again. And then also when you get to the quiz, there are some additional videos provided on a lot of these problems. So good luck on that. And we'll see you in class with, no, I'm not done. Sorry. I forgot. There's a couple more sections. So this is the basic, this is the meat of it, but there's several other statements that we can derive from the conditional. So inverse, converse, and contrapositive statements are all conditional type statements, but they're derived from rearranging, switching stuff around. So let's look at this. P implies Q is the original. If that's the original statement, I could discuss or talk about another statement. The converse of P implies Q is Q implies P. So that's a specific type of statement. So if the original is true, is the converse true? We'll see. And then another kind of statement, the inverse, is called not P implies not Q. That's the inverse statement of the conditional. And the contrapositive is not P implies not Q. So part of the skill here is parsing what these are. So let's practice with maybe A implies B. What's the converse of A implies B? Use the pattern here. It switches them around. B implies A. What's the inverse of the statement? That would be not A implies not B. You can see the pattern here. And the contrapositive is not B implies not A. Let's have some practice. You'll see in the quiz. And so let's apply this to a sentence. If it's raining, then there are clouds in the sky. The converse would be, which this statement is true. If they're raining, there's got to be clouds. I mean, there's one time I've seen rain and there wasn't clouds directly above me, but there are still clouds in the sky. So the converse of that statement is if this is P and Q, we switch them. We say Q implies P. If there are clouds, then it's raining. Not always true. It could happen sometimes, but there are exceptions to this. So this statement is not true. Let's look at the inverse now. The inverse says, hey, not P implies not Q. That would be it's not raining and there are not clouds in the sky. That could also be true, but it may not be true. There could be clouds and not raining. So clouds and not raining would disprove that. And then the contrapositive is example, if there are not clouds in the sky, then it's not raining. That statement, if you think about it, not Q implies not P. That is true. There are not clouds in the sky. Anywhere in the sky, it cannot be raining. So I think this is a really good example to see how the conditional, the original statement, the conditional, the equivalent to the contrapositive. We want to be careful and build the truth table for the contrapositive. You'll see it's exactly the same as the conditional. It's very interesting. The contrapositive and the conditional are saying the same thing, just in a different way. And then if you look at the converse and the inverse, they end up being logically equivalent too. I don't know if we want to do this. No, you can actually build these truth tables yourself and see that. Very good activity to see if those are equivalent. So let's just look at an example that applies this. If I eat this giant cookie, I will feel sick. I cannot have very much sugar. I will feel sick. What statement is equivalent to this? This is P implies Q. The equivalent statement would be the contrapositive. So not Q implies not P. So that would be, I don't feel sick. If I don't feel sick, that's not Q. Then I didn't eat the cookie. That must also be true. If this statement is true, this statement is true. Very nice. So that's very useful. Okay, it's getting a little bit longer than I hoped. So negating the conditional, this is something that we kind of already talked about. And so I want you to look at this question here. See if you can interpret that with your own thinking. If I park here, then I'll get a ticket. That's what my friend tells me. What if I want to prove him wrong? I don't recommend it, but if you want to prove him wrong, what you have to do is park here. So if this is P implies Q, you have to park here and not get a ticket. Then you prove him wrong. So you parked here and didn't get a ticket is a way to negate the conditional. So I'm just going to write it like this. Not P implies Q is the same thing as P and not Q. And here's a task. Maybe we'll do this in class. If you write both of these statements out, both their truth tables, they're logically equivalent. They have the same truth table. That's one way to tell if two statements say the same thing. If they have the same truth table, they have to be the same, because in every outcome, they have the same logical result. Okay. So lastly, last section is another logical operation that is really just a combination of two conditionals. So we have P implies Q, and it's converse. If both of these are true, then we can say P if and only if Q. P if and only if Q. This is read if and only if Q. And it's the same thing logically as saying P implies Q and Q implies P. So if you want to find out the truth table for this, that's a really good task. Here's what it is. Ends up being when both P and Q are true, it's true. When both P and Q are false, it's true. And when they're opposites, when they're not the same, they're false. They're not the same when they're not the same. So here's an example. I wear my running shoes if and only if I'm exercising. This means if I wear my running shoes, I'm exercising. And it also means if I'm exercising, I'm wearing my running shoes. So you can use that to say that if I'm exercising, oh man, now this is getting me confused. I'm exercising and I'm not wearing my running shoes. Okay, that would be P and not Q. No, this has got to be false. What about I'm wearing my running shoes, I'm not exercising. So I'm wearing my running shoes. Well, one of them's false, one of them's true, so that's got to be false. But not exercising and not wearing my running shoes would be true. So that's a good way to think about it. Okay, I should stop here. I hope you enjoyed this. I think logic is super fun. It's super cool. So hope we get some more of that from us in class when we get together for questions. So we'll see you in class. Good luck.